Thank you for joining us today. This is the fifth of a series of project webinars. As folks may know online that the prior webinars have been saved on our YouTube channel. So I encourage people to look at past issues as well as enjoy today's proceedings. Should you prefer the webinar in French, you can use the same video link. The instructions are to mute your sound on your computer and join by teleconference for the French translation. The dial-in number is 1-866-513-2325, extension 2100, and when prompted, enter conference ID number 5028127. This is our first daytime broadcast. Normally we have these presentations in the early evening, so we would really be interested in hearing feedback on the timing of today's update and how that works for other people participating schedule. And also by way of a reminder, participants are welcome to submit questions during the presentations, and we will respond to all questions at the end of the second presentation. I'll point out that loading the questions earlier is helpful because there is a brief delay here so that we don't have this long pause waiting for questions to come in at the end of both presentations. That is helpful. Today we will be hearing from the NPD project first, followed by NSDF. Both projects will be providing an update for participants. And right now I'll turn it over to Kristen Schroeder.
Thanks a lot, Pat. Good morning, everyone. My name is Kristen Schroeder, General Manager for Reactor Decommissioning, and with me today I have Andy McVeigh, who's the NPD Health Physicist. Today we're going to be talking about calculating the waste inventory for the new NPD disposal facility. Can you go to the next slide, please, Andy? So just a reminder of what our proposal is. So this is just a proposal. We are going through the regulatory process right now with the Canadian Nuclear Safety Commission. But what we're proposing for the NPD facility. So if you remember, the NPD facility was Canada's first demonstration CANDU reactor. It shut down in 1987, and we've been safely maintaining it for the last 30 years in storage with surveillance. We are looking forward to move forward with the next phase of decommissioning. Proposing is actually to create an on-site disposal facility and leave all the remaining material there on site. Now there's the key thing about this facility, as you see in the top left-hand corner, is that this facility is built below grade. It extends 80 feet below grade and is anchored into bedrock, and the reactor itself is actually 45 feet below grade in bedrock. As part of our initial shutdown activities, all the fuel has been removed from site, all the systems have been drained, and all that remains now are the tanks and systems and empty tanks and systems that previously were there to support the operation of the reactor. So as you can see from the middle photo, what we're proposing is to use a specialized grout. This facility, the foundation walls does remain in the facility, so that is not required for the disposal facility. We're actually maintaining that stack for the chimney swift, an endangered species that roosts within this stack. Now the important thing to note is that we're not bringing any waste from off-site to this facility. It's only the existing structure that's there. If we can go to the next slide, please. So as Pat pointed out, this is the fifth in our series of webinars that we've been doing. And in The topics that we've chosen for our webinars are based on some of the comments that we received from the public and Indigenous groups as part of their review on the environmental impact statement. So as Pat pointed out today, and we're going to be talking about our waste inventory, it is a little bit more technical than our usual ones, but it's important that you understand how we verify the inventory that will remain inside the facility. I'm going to pass it over to Andy McVeigh, and he's going to walk you through our presentation.
Thanks, Kristen. Hi. So I'll go into a little detail on why and how we calculate the waste inventory, the approach the NPD closure project has taken to achieve a solid understanding of this waste inventory, and some of the answers to those first two questions are what kind of waste, both hazardous and radiological, and how much of each of those kinds of waste is at NPD. So the end state for in situ decommissioning, as Kristen already spoke to, will result in a disposal facility. The waste inventory is required in the long term to inform post-closure safety assessment as a contributor to the safety case, to make accurate predictions of how the disposal facility will perform after closure. In the short term, we need to know the radiological inventory to ensure our decommissioning plans are protective of workers, the public and the environment. Using information gathered from historical records, include operational records, the existing calculated inventory and records generated during the quiescent storage period, such as radiological scoping surveys. The characterization plan could be drafted, enabling a detailed characterization of the facility. The goal of the characterization plan was to establish a bounding source term, which means that the emphasis was to gain a conservatively high estimate to feed into the safety case, as well as to break the contributing components down by structure or system to form the resulting waste database after the disposal facility is closed. To get a detailed waste inventory, existing data were verified by conducting extensive characterization activities, including sampling the reactor components, internal samples of the nuclear systems, as well as systematic surveys and sampling of the building infrastructure itself. All of this was used to verify that the modelled or calculated source term is indeed bounded. So the main sources of guidance, as well as the relevant standards, are the two CSAs on general principles for management of radioactive waste, as well as the guidance document on clearance and exemption. Other important guidance, due to their precedent rather than their authority, was the adoption of methods and techniques that can be found in the Marsane US NUREX. These provide the defensible statistical basis for characterization planning. Also the IAEA safety reports, number 95. This provided guidance and precedent on the approach and the methods used to assess the largest fraction of the radiological inventory, which is the reactor block. Oak Ridge Associated Universities, planning for characterization was performed in consultation with Oak Ridge. They produced the historical site assessment, which is effectively the first stage of characterization planning and involves conducting a site investigation to describe the physical site, identify release mechanisms, and any potentially affected media. The second stage is the use of this information to assist in the generation of the characterization plan, which was also written by Oak Ridge. This now designs the characterization surveys and sampling plans to conduct in order to meet the desired planning targets in terms of establishing upper confidence limits of the mean results. In order to facilitate what was a great deal of work, a contract was established between NPD and Oak Ridge to provide training against the characterization plan that they had just drafted for us. This involved NPD staff as well as other staff from appropriate business units around the CNL site who came together to conduct the training, and after approximately 2 weeks, a large amount of the characterization work had been completed by approximately 20 staff. The remaining work, when that was complete, was sample analysis, survey results, interpretation of information, and that fell to CNL to perform. But the bottom line was that we carried out a process based on best practice across the industry, and we sought external expertise. The two distinct contributors to the radiological industry are the activity which is induced in reactor components by neutron activation, and this largely remains embedded within the materials exposed and confined to the reactor vault. But also there's that of contamination, which comprises fission products released by damaged fuel, as well as the previously mentioned activated materials, which are now subject to corrosion effects. This mobilizes them and enables them to be circulated around the systems, which effectively means that they are available outside of the reactor vault and can be spread by leaks and spills and other operational occurrences over the lifetime of the reactor. The activated reactor components comprise approximately 99% of the radioactivity, with the remaining 1% being that attributable to contamination. The waste verification activities undertaken broadly broken down into three characterization efforts. As I mentioned, we sampled the reactor components for verification against the existing source term, which was established in 1988, shortly after shutdown. We carried out intrusive sampling of nuclear systems, as well as all the associated minor and subsidiary systems, and including standalone equipment such as fuel handling equipment, and survey and sampling of the facility infrastructure throughout in order to confirm residual radioactive contamination, as well as conventional contaminants that may be of concern, classified as hazardous, such as PCBs, asbestos, and heavy metals. So the diagram on the slide shows how the radioactive inventory was also compartmentalized for the purposes of the post-closure safety case modeling. The inputs to this model were the radiological inventory placed in the appropriate modelled box, along with other waste attributes, the physical attributes such as mass and density. The other purpose the characterization was to inform was the resulting waste database for what will become a waste disposal facility, but this entails a compilation of similar information. This slide describes some of the quality assurance and quality control measures that were implemented over characterization. As I've already mentioned, the original source term was calculated in 1988, but this was verified in 2012 using updated models and libraries to contribute to the computer model. The reactor inventory was then recalculated from first principles using a later version of the origin code. And a further code used Monte Carlo processing in order to effectively become a three-dimensional replacement for the original source term, which was based on a one-dimensional model. Survey instruments are checked with increased scrutiny during calculation, mainly due to the quantity of information that they log and the potential rework that would be required should a calibration wander or an instrument become damaged. Sampling error is reduced as far as possible during work by careful consideration of cross-contamination, as well as a good control of samples by assigning unique identifiers and a prevailing understanding of chain of custody requirements from all workers concerned. Lab accreditation and qualification is confirmed at the procurement stage, and any calculation or assessment of is reviewed by competent technical reviewers, which was especially important due to the size of the data files that were created by the analysis results. Hazardous substances, as mentioned, in assessing the levels of hazardous substances, it was already known that lead paint was used throughout the facility, but it was also present in bulk quantities used structurally as shielding. Residual mercury was expected due to damaged electrical components, PCB containing light ballasts, which will all be removed before closure, were known to exist. And asbestos insulation on nuclear systems has largely been remediated, but this will be returned to the facility before closing as waste packages. So to understand the potential for a release of lead into the environment post-closure, it was important to understand the distribution of lead within the facility, and given its solubility level, how and when water contact would result in a release. So to that end, this slide defines on the left-hand side, the initial lead inventory, with the effective resulting lead inventory on the right-hand side, and how it relates to the modelled compartment shown earlier. As with lead, asbestos, PCBs, mercury, similar situation. On the left-hand side, we have what was initially known, and on the right-hand side, what will be residual within the facility on closure. So, for confirmation or verification of the radiological inventory, as I said, reactor sampling was a big one. A company were engaged to collect the requisite samples, which were set by the characterization plan, and this called for 3 representative samples of each material or component. Sampling was undertaken as shown in the schematic drawings, the schematic using a 5-meter long drill bit to penetrate the concrete shield and then beyond to penetrate the various vessel components as the drill advanced. Samples were obtained by pulling a vacuum back via the drill bit to a collection device as the drill traversed the various materials, using precise measurements of the bit's travel, as well as feedback through the equipment to the operator. He or she is able to then divert the spoil created to a series of pre-labeled collection points. Not all samples were obtained due to operational setbacks, but certainly enough were taken to achieve the objective. And where there was a shortfall in sampling requirement, and where it was unavoidable, additional lines of evidence were used to fill that gap, such as comparing the observed gamma radiation levels measured within the reactor vault to those predicted, and also comparison and decay of results obtained with small-scale analysis taken on removal of components in 1986. All the samples collected were then sent for analysis under chain of custody arrangements, and the results written up into a report which compared the observed results with the existing estimate. As I mentioned earlier, the modelled inventory was recalculated in 2018-19, mainly due to concerns from the regulator as to the applicability of the calculation as it was performed using older one-dimensional codes and aging libraries. And so CNL reactor physicists who performed the 2012 verification were engaged to recalculate this from first principles. The changes noted were a revised power history for the reactor, updated and revised material specifications, and an improved understanding of impurity concentrations, the use of updated code and libraries for nuclear cross-section, fission yields, nuclear decay data, and other information as such. And also, as I mentioned, Monte Carlo code, MTMP version 5, was used for the transport code, which effectively results in a 3D output. So this table shows the results of the reactor components sampling and assessment. The initial pre-characterization total reactor inventory, estimated by Origin Code in 1988, is the middle set of figures there. The field calculated activity, i.e. that obtained by sample, showed this estimate to be conservative by at least a factor of 2. The subsequent recalculation is the column on the far right there, and that shows that the sample data was then further conservative by approximately 5 times. But what was actually carried forward to be the reactor volt total was a composite total, whereby the higher of either the sampled or calculated results for each radionuclide were used to add to the total for each component material. And the final total was that figure over on the right that you see there, 7.51 times 10 to the 13 becquerels. The exception to this precedent was for tritium, which was hugely overestimated in aluminium, but conversely underestimated in the concrete. But that offset is why the composite result is slightly less than the actual calculated data. So moving away from the reactor volt, we have the two primary nuclear systems of the moderator and the heat transport system. To characterize these systems, we wanted to minimize risk to workers and therefore the burden of sampling. So a two-phased approach was to collect samples at judgmental locations such as hotspots, impact and transition areas likely to be an area of held-up contamination, in order to establish a fingerprint and obtain a correlation to the gamma radiation emitting radionuclides at the point where the samples were taken. When results were returned, we were able to model the section sampled and obtain a correlation to the system content by external dose rate of the cesium-137 content. Then using a rank set sample plan involving measured gamma dose rates on contact with the piping and the various elements of the system at 14 locations randomly generated along the length of the system. This we could then infer the gamma emitting content using the dose rate and then apply all the hard to detect radionuclides in the applicable ratios obtained in phase 1 sampling. This gave us a mean average concentration internal to the system, which we were then able to apply over the entire at-risk internal surface area. So this diagram just briefly shows how the building infrastructure itself was broken down by classification as per the MARSIM or the US New Reg. The green area are class 3 areas, which means there is a potential for contamination. The blue areas are class 2, which means that the areas are possibly contaminated. And red is a class 1, which means we already know that there is contamination or that there is a high likelihood of contamination. Now what this hierarchy of classification does is changes the quantity and distribution of sampling that is required in order to achieve the desired upper confidence limits. The red class 1 area in this case is the reactor hall, which is directly above the nuclear area of the facility, and also allowed access for fuel transfers, etc., and hence the class 1 label. So this is the reactor hall again, and this is an example of the sampling plan that was generated, the output of which is annotated with coordinates from which workers can identify an appropriate sample point. At each of these sample points, alpha, beta, and gamma radiation readings are taken. They are normalized against their respective background readings, and these points are ranked in terms of high, medium, and low results. For each set, a high, medium, and low point are selected to be sampled. This was a 3-set plan, which means we end up with 3 samples of each rank. Additionally, a scanning survey took place to identify any areas of elevated activity that might be missed by these sample points. Anything noted is also collected as a judgmental sample, and this is added to the inventory of samples that are assessed. As I said, these samples are then bulked to represent the individual room or survey unit and sent to an accredited external lab for full isotopic analysis. So the bounded source term for the post-closure assessment has been established from acceptable sources with conservative assumptions. The radiological inventory at NPD is well characterized. beta-emitting activation products being the primary long-lived radionuclides. And the characterization plan is to provide a defensible process for verifying waste, while the waste database will accumulate the inventories for comparison to the bounding source data. But the bottom line, we know the waste, we're confident that our decommissioning plans and our post-closure safety assessment are protective of the public, the environment and the workers.
Thanks, Andy.
So any questions? Because I know I rushed through and covered very scant detail, so please let us know if you have any questions and we'll do our best to answer.
Thanks, Andy. Over to you, Megan.
All right, thank you, Andy. So good morning, my name is Megan Vickard. I am the director for the Near Surface Disposal Facility project. And with me, I'm joined by Sandra Fott, the regulatory approvals manager. Today, although NPD provided information on the characterization of their inventory, for NSDF, we are going to provide a bit of a different topic because we do have some very important news to share with you with respect to the project. As Chris and Pat have mentioned, this is the 5th of our webinars where we have focused the topics of each webinar based off of public themes or public areas of public interest. And today, similar to that, we would like to talk to you about some important news and some availability of new information that we have produced. So if you recall, CNOW, we have submitted the draft environmental impact statement for the Near Surface Disposal project back in 2017. That draft EIS underwent a review by the federal and provincial agencies, as well as was available for formal review by the public and Indigenous groups. The NSDF team, since receiving all of those formal comments, has been very busy for the last 2 years addressing and revising the documents, the design, updating assessments and modeling, and ensuring that we incorporate the feedback that we've received. Today I'm very pleased to announce that a revised draft EIS is going to be available by the end of the week on our website. And that's going to be the focus of our presentation today. I will briefly remind, for those who might be new to the Near Surface Disposal Project, what Near Surface Disposal Project is, why it's needed, and a bit of information about what an EA is by Sandra. Sandra will also review some high-level changes that have been made in the revised draft EIS to incorporate feedback from the public. And we will end with telling you where you can find the revised EIS later this week and some updates and changes that we've made to our project website. So as a brief reminder, CNL, Canadian Nuclear Laboratories, is contracted by ACL to operate and perform a cleanup mission for a number of sites that ACL is responsible for throughout Canada. That includes the Whiteshell sites and the Chalk River site here in Ontario. A brief history or reminder about the history of the Chalk River site is that it is a very complex history. It was the birthplace of the nuclear industry within Canada. With that came a lot of very important research and industry and groundbreaking work done, including the production of medical isotopes that have been used in diagnostics as well as cancer treatments. However, with that great research and development that has been done at the Chalk River site, that work has also produced waste that the Government of Canada is responsible for. ACL manages and has contracted CNL to provide solutions for. So what is the Near Surface Disposal Facility? Currently, it is a proposal. We are going through the environmental assessment process as a proposed solution for how we would address the Government of Canada's liabilities and responsibly manage its radioactive waste, in particular, the low-level radioactive waste. What will it look like? The Near Surface Disposal Facility includes a number of components. First and foremost is the engineered containment mound, which consists of engineered systems such as a base liner system and a cap and cover system, which has a number of components in it, including primary and secondary leak detection and collection systems, as well as engineered barriers to ensure proper containment of the inventory for as long as necessary. And we'll talk a little bit about that. The near surface disposal facility engineered containment mound will be built in 2 phases. The first phase ensuring that we manage all of the waste that we currently have already generated, the legacy waste, as well as handle waste that are going to be produced as a result of our cleanup missions at the White Shell and Chalk River sites. Each phase will have a series of disposal cells which will be operated where waste will be compacted in place and covered as it is filled. We do expect that due to rainfall or snow, that precipitation will infiltrate the waste and create leachate, which we do collect and convey to our wastewater treatment plant, where we will remove contaminants from the leachate or wastewater and ensure that before we discharge the treated effluent, that they meet the target effluent discharge criteria, which we have identified as either federal or provincial guidelines to ensure the protection of the environment as well as the public. What will go into it is only low-level radioactive waste, solid low-level radioactive waste. And what that looks like is general items such as trash or debris that we generate on a daily basis, such as our PP&C or personal protective equipment and clothing that becomes contaminated as a result of our operations. But more significantly, what will go into it is waste generated as a result of our cleanup machine, including impacted soils and demolition debris during the revitalization of the Chalk River site. Low-level waste primarily contains short-lived radioactivity and limits or restricts the amount of long-lived radioactivity, so it does decay very quickly. How we're protecting the Ottawa River includes the collection of the leachate, but also most importantly is the site that we've chosen at the Chalk River site is protective of the environment, and especially the Ottawa River. The proposed location of the near surface disposal facility is on a topographic high at the Chalk River site on a bedrock ridge, which naturally forces groundwater away from the Ottawa River. Plus, we have a number of engineered defenses or passive engineered barriers that we have designed to ensure the proper containment of the inventory. Among those, I've already mentioned that there's going to be a final cap that includes a number of engineered components, including a geosynthetic clay liner and a geomembrane liner. The base liner includes primary and secondary leachate collection systems, as well as double systems of geosynthetic clay liner and geomembranes. The geomembranes, we have conducted some extensive testing to demonstrate that these man-made or synthetic components can last for 550 years, and actually some of the test results indicate that some candidate geomembranes can exceed that and last for upwards of 2,000 years. That was a previous webinar that we presented and is on our project website. In addition to the man-made or synthetic components, there's also natural materials such as a compact clay liner, which is a proven material to ensure hydraulic barrier or limit the infiltration of water through it for thousands of years. In addition, I've already mentioned the wastewater treatment plant, that our leachate collection, conveyance, and treatment system is designed to ensure that we collect all wastewater generated at the near surface disposal facility. We are taking measures in the design and operation of the near surface disposal facility to limit infiltration or contact with rainwater or snow, such as covering the waste as each disposal cell is filled, and only operating one disposal cell at a time. However, the contaminated wastewater is collected and managed through our wastewater treatment system, and we have conducted pilot testing to ensure that the design basis and the simulated leachate that we've predicted will remove contaminants to the the effluent discharge targets that we've set for ourselves. We get a lot of questions, what ifs, a number of environmental events, such as an earthquake, a flood, a tornado, and what if in the future a farmer or an animal digs into the mound. Well, I want to assure you that the facility has been designed with a number of events in mind, such as tornadoes, floods, and earthquakes. We've already talked about the elevation of the facility being far above the floodplain elevation of the Chalk River by at least 50 meters. The facility has also been designed, take into consideration an extreme seismic event that would only happen once in 10,000 years, and that the facility has been designed to ensure integrity and containment of the waste in such an extreme event, an event that's never actually happened in the Ottawa Valley. So when will this all happen? I just want to remind you that this is only a proposal right now that we have submitted to the regulator and the responsible authority for the environmental assessment process, the Canadian Nuclear Safety Commission. So right now we are at the stage of a proposal. The CNSC would render a decision after a commission hearing process where the public has more opportunities for formal engagement. 2 decisions will be made, one on the under Canadian Environmental Assessment Act and one under the Nuclear Safety and Control Act. Once a decision is rendered, if we are successful, the facility will go into, the project will go into the construction phase for a couple of years, following which we would enter into a period of operations for at least 50 years. And the intention is that the facility is being built to accommodate all projected waste, low-level reactive waste, that CNL would be responsible for during that time frame. After the facility is complete, its operation or it's full, the facility would be closed with a final cap and cover and restoration activity. We would go into a period of monitoring and surveillance, and we would control the site from an institutional perspective for as long as the regulations require us to, or as long as we're required by the regulator who will oversee our operations. But for planning purposes within the environmental impact statement, we have used a time frame of at least 300 years. At this time, I'd like to hand it over to Sandra, who is going to speak a little bit about what an environmental assessment actually is and what changes you can expect to see in a revised draft environmental impact statement.
Great, thanks Megan, and thanks to everyone that's joining us this morning. So just a little update or reminder about what an environmental assessment is. So the Near Surface Disposal Project is considered a designated project under the Canadian Environmental Assessment Act 2012. Some of you might be aware that the new Impact Assessment Act did come into force this fall, in fall 2019, but there are provisions in the Impact Assessment Act for projects that were already underway to remain under the current regulatory process. So the NSDF project does remain under SIA 2012. In conducting our environmental assessment, we have followed generic guidelines that are put out by the Canadian Nuclear Safety Commission, as well as guidelines that are given to us from SIA. Megan already mentioned that the CNSC is the life cycle regulator and will consider this environmental assessment in all licensing decisions. So some of the main points of doing an environmental assessment is to look forward as to what will happen while the project is happening, as well as when the project ends. So we look at the environment as a whole. So we look at soil, we look at air, we look at water, we look at people, workers, and the public. We must reflect input from communities, including Indigenous communities. And this is actually the topic for today's presentation. We look at alternative means of conducting the project. So this included alternatives for the facility location, the site location, the facility design, as well as different options for effluent discharge. And we also have to consider the potential for cumulative effects and overall assess the significance of residual adverse effects. Next slide, please. Thanks. So the 3 sources of comments that we received on the draft EIS in 2017 were from the public, from Indigenous groups, as well as federal and provincial reviewers. So there was a similarity among all reviewers in a lot of the themes that we heard. So we're just going to touch briefly on some of the main themes. So from the public point of view, there were a lot of questions around justification for the project, the waste inventory, the design and engineering, alternative means, environmental events, protection of the Ottawa River, follow-up monitoring program, transparency, and availability of documents. We're going to touch on a few of these today, but we're always open to meet with anyone at a convenient time for them to further discuss any of these topics. The Indigenous Peoples Review covered again many of the same topics as the public, but things that were unique to the Indigenous Peoples Review were incorporating information from a traditional land and resource use study. We have incorporated the results of one such study into the draft EIS, valued components that were important to Indigenous peoples, as well as information on the follow-up monitoring program. From federal and provincial agencies, there were a lot of questions around the waste inventory, environmental events, the safety assessment, and that includes both operational and post-closure. Both of these safety assessments have been updated and will be made available, as well as the overall design. So just to touch on a few of the main topics on what's changed from 2017 to today. We talk a lot about the reduced waste inventory. So the NSDF project will only include low-level radioactive waste. So the waste inventory has been reduced by about 97% since the 2017 draft EIS. With the definition of low-level radioactive waste from the CSA standard N292, we're using the lower ranges of the definition of low-level waste. We've also revised both the reference inventory and the waste acceptance criteria. So basically the compliance with the waste acceptance criteria is CNL's responsibility, and if inventory doesn't meet the waste acceptance criteria, it will not go into the NSDF. There will be oversight by our independent regulator, which is the CNSC. Just for people's information, the intermediate level waste that's currently being stored at Chalk River will continue to be safely stored until another option is available in the future. So we also want to emphasize that the NSDF is an environmental remediation project. ACL, now CNL, has been making advances in nuclear science and technology for more than 70 years. As Megan mentioned earlier, this proud history has created liabilities in the form of waste. The past waste management practices met the standards of the day, but has led to impacts in localized surrounding environment. So the NSDF will provide a permanent, safe disposal in a manner protective of the environment and of people. One of the things that we heard was around the regional study area for the near-surface disposal facility project. You may recall that the regional study area in the 2017 version of the EIS ended at basically the mouth of Perch Creek at the Ottawa River, so did not include very much of the Ottawa River. So the revised EIS has been expanded to include the Ottawa River 8 kilometers downstream of the Chalk River site, including both the Ontario and Quebec borders. The results of this have been modeled for surface water as well as the aquatic environment, and ultimately there is no significant adverse effects on the Ottawa River as a result of the NSDF project. We've also completed a number of baseline studies since 2017. We've done fish studies of Perch Lake and Perch Creek. We've looked at sediment in Perch Lake, as well as done a bathymetry study. We've also installed over 30 new groundwater monitoring wells on the site of the NSDF. So this all helps us understand the current environment and helps us further model any predicted effects that the project could have in the future as a result. So we've also been working hard to understand impacts on species at risk. And I'll touch briefly on two species, the bats and the Blandings turtle. So since 2017, we have been doing a maternity roost study with Trent University and Ministry of Natural Resources. The white nose syndrome is having a great effect on the bat population here in Ontario in general. So as a result, we're learning more about where bats like to roost and how we can mitigate those effects within Chalk River, as well as the NSDF project. One of the things that Chalk River as a whole is doing is working on a sustainable forest management plan. This plan will be for the entire Chalk River site and not just for the NSDF project, but it will help understand how to better protect the species of bats found here at Chalk River. As well, with regards to turtles, the Chalk River site is implementing a turtle road mortality mitigation plan, in particular for the Blandings turtle. So this includes the installation of new culverts, fencing, specific turtle fencing for along the roads, as well as the creation of habitat for nesting. So with these two things, overall, the NSDF project will not have any significant adverse effects as a result. There is specific mitigation measures that will be undertaken by the NSDF project that are outside the Chalk River plans, but overall, no significant adverse effects on bats or turtles. We touched briefly on the post-closure safety assessment, and so we looked into the future to see what might be affected once the facility closes. So the post-closure safety assessment has taken into account the scenario where somebody builds a house on top of the NSDF, puts a well in, gardens, has livestock, has recreational hunting and fishing. We've also looked at off-site cottagers downstream, as approximately 8 kilometers downstream, as well as further downstream into Ottawa and Gatineau. And we've looked at Indigenous groups as a self-sufficient group that is living in a traditional lifestyle, so gathering and hunting and fishing and living off of the land. And the results of this results in very low dose, well below regulatory limits, and so that gives us confidence that the inventory will not cause any effects in the future as a result of the NSDF project. We've also added a section in the revised environmental impact statement focusing on Indigenous interests. So CNL has a memorandum of understanding, and with the Métis Nation of Ontario, as well as the Algonquins of Ontario, and we have been providing capacity for traditional knowledge and land use studies, as well as providing information on the revised EIS. And with that, I'm going to turn it back to Megan. Oh, no, I'm not. So this is just a general slide that shows some of the things that we have changed since 2017. The items that are in bold are the ones that I just spoke about, but the other, there's a lot more on the list. So again, if anyone ever wants to speak further about these topics, we're always welcome to talk to you, as well as they've also been the topic of previous webinars.
Okay, thank you, Sandra. So you'll go, as we mentioned, the revised draft EIS will be available for your review later this week. We are releasing it before the end of the week, and we will notify everyone through emails or on our website or through social media. You will find the revised EIS on the project's website at www.cnl.ca/NSDF. You'll see that the website has been revised to ensure that the revised draft EIS announcement is the top of the page as the first link, so that it'll be very easy to access, as well as a couple new items on the web page explaining where we are in the regulatory process. So in addition to the revised EIS, the EIS is a culmination of up to 15 technical support documents. Those are go into details and about the modeling or assessment or design work that was done, and the summaries can be found, the summary of all that work is found in the revised draft EIS. So we are making available all 15 technical support documents if you would like to get into the details of how the modeling or design work was completed. So this diagram just shows how each of those technical support documents feed different aspects of the environmental impact statement prepared. So I just want to point out that where we are in the regulatory process is we're still at the period where we are addressing all of the technical concerns from the regulator and the regulatory agencies, as well as the public and Indigenous peoples. What we've produced is a revised draft EIS. It is not the final. The final would be submitted after the regulator or responsible authority, the CNSC, identifies that we've addressed all technical concerns. So this is a revised draft that we are voluntarily sharing with the public because we do want to recognize that we value all the feedback and comments received, and that has led to some revisions in the draft EIS that we would like to discuss with you one-on-one. I do want to note that you'll notice on our timeline that we are recognizing that it is likely that the near surface disposal project will be a two-part commission hearing, not just a one-part commission hearing. So that decision and the timing and date of those commission hearings would be announced by the CNSC once the final EIS is submitted. So in final words, I just want to recap that we are making the revised draft environmental impact statement publicly available to ensure openness and transparency of all of the work that we've been doing in the last 2 years. And so it gives an opportunity to the public to have a look at what changes we are proposing in the final environmental impact statement. The EIS and the technical support documents will be available later this week on our project website. Any key milestones or updates about the project will be shared with public and Indigenous peoples through social media or direct emails. We will continue to engage and communicate on what changes have been made as a result of the comments that we've received on the draft EIS. We look forward to meeting with you, or if you would like to reach out to us to meet and discuss the revisions, we would be happy to do so. So make sure that you stay up to date on the near surface disposal project through our regular webinars, such as today's, through breakfast briefings, or on social media. So thank you very much, and we're open for questions.
Thank you very much for the projects, and thank you to the participants. We notice that the queue for questions is loaded. I believe for all, the first question has been addressed. The near surface disposal facility project will be releasing its revised draft EIS later this week. So that, I believe, addresses the first question. The next question and next several questions are for NPD.
Okay.
Algonquin Valley asks how much, and roughly, of course, of the NPD and NSDF technical work was performed by CNL staff versus contractors.
Sure. I'll talk about NPD first. Just touching on the topic that we talked about today, characterization. As Andy pointed out, we utilize contract support to help us prepare the characterization plan, as well as to take the samples for the reactor itself, and then we use CNL staff in order to do the remaining characterization activities, as well as writing the reports. We also used labs, so contracted labs, in order to do some of the sample analysis. Just looking at other technical work, we're working closely with Arcadis to prepare the technical and environmental assessment documents. So that's kind of a joint effort between both groups. As we look into the future, we'll be self-performing some of the demolition work and outsourcing or contracting some of the work, such as the concrete cap and the engineered barrier. Thank you.
Yep. So for what I can add is for near surface disposal facility, we also make strategic decisions as to how to involve the expertise of contractors and consultants. For the near surface disposal facility, we have utilized ACOM to produce a design for the near surface disposal facility, as they have been designers of many facility designs in the US and within Canada. We have also used Golder to prepare the technical environmental impact statement, as well as have some other subs such as Arcadis as well to perform the long-term dose modeling or pathway modeling, which is the post-closure safety assessment and the ecological risk assessment. And in the future, we do anticipate on using contractors to construct the facility.
Okay, thank you, Project. And actually, these next 3 questions are for NPD.
Great.
Ole has asked, how do you verify estimates of non-radiological contaminants, lead, PCBs, etc.?
Okay, so during the presentation, I showed you a copy of a sampling plan for the reactor hall. That was obviously just one room, one location within the facility. That precedent is repeated throughout the facility, and effectively that resulted in almost 200 samples of the building infrastructure. These are then bulked and sent for lab analysis, not only for the radiological content, but also for PCBs, heavy metals, lead. In addition to all of that, we also took judgmental samples of all the various paint coverings in the facility and any caulk or anything else that judgmentally stuck out is requiring analysis. And as a result, I think we got pretty robust coverage of the whole facility.
Great, thank you, Andy. The next question, again from Ole, did you succeed in getting any pressure tube samples?
We did. As I said, we engaged a contractor for this task, and they did very well, and they obtained almost all the samples we asked for, or we strived for. The pressure tubes, if you think about it, are the last sample as you drill through that concrete, and so we've gone through traversed various parts of the reactor. We've got 2 shells of the calandria, we've got the calandria tubes, the steel vault liner, and the concrete. And it was at this point that we encountered difficulties. We did obtain 2 individual samples of pressure tube, but that was the gap that I spoke about, and we did use additional lines of evidence from pressure tubes removed in the 80s in order to verify against the calculated inventory. So we did fill that gap.
Okay, thank you. The next question for NPD, again, comes from Ole, and I know this has occurred towards the tail end of your presentation. It asks about what is the difference between potential and possible?
Yeah, I think I recall stumbling over my words somewhat there, yes. The Class 3 areas were designated Class 3 because they had a lesser potential for cross-contamination from the Class 1 impacted areas. The Class 2, I think I used the word possible, but it's just a graded approach, and therefore it was still likely, but more likely than the Class 3s, and hence it drives the sampling requirements as such.
Okay, thank you. Moving on to some NSDF questions. We have 3 here. Again, the first from Ole. You mentioned effluent targets that you've set for yourselves. Should not there be an independent validation of those targets?
Sure, so I'll start and then Sandra can add in. So first I just want to clarify the effluent discharge targets are established as part of the design process. So we establish targets for ourselves to ensure that the treatment process that we design has an objective for removal of contaminants. And then we make sure that we test it with bench scale testing. So the targets are design targets, and then it's with respect to that's what the near surface disposal wastewater treatment plant would release. Now, as far as cumulative releases from the Chalk River site, those are controlled under our license, and those are independently verified by the regulator, the Canadian Nuclear Safety Commission.
Yeah, and I'll just add that our effluent discharge document is available on the website currently, as well as it will be available later this week. The effluent discharge targets have been based on either the Canadian Council of Ministry of the Environment or Ontario Provincial Water Quality Objectives for non-radiological COPCs, whatever was more restrictive. And for radiologicals, we are using Health Canada drinking water standards.
Thank you for that. Our next question comes from Algonquin Valley. What would be done if filled and covered cells continue to release high levels of contaminated effluent indefinitely?
Okay, so again, I can start, and Sandra can add anything. But just a correction, since near surface disposal facilities waste acceptance criteria is only for low level, there would be no high levels amounts of contamination that's in our leachate or effluent. It's all low levels. We do have a wastewater treatment plant, and the treatment plant would continue to operate as long as necessary, for as long as the disposal cells are producing appreciable quantities of leachate or wastewater. So the wastewater treatment plant would continue to operate and treat and remove the contaminants, even after this closure of the cells.
Thank you. Larissa asks, when you say that each cell will be covered as they are filled, can you explain the type of cover? Will this be an impermeable cover?
So again, I can take that. So the covers that we will use as each cell filled, we call them interim covers, and yes, they would be impermeable. And you can find more details. We acknowledge that the draft EIS was not very clear in the filling or operation during the filling of the cells. So the revised draft EIS in section 3 has more detail about the different cover systems and when they would be used during the operation of the near surface disposal facility. So there's definitely more details in the EIS that will be released later this week.
Okay, thank you. And I believe we're at the final question that we have here so far. Tom has asked for NSDF, how do you propose to remove tritium from the leachate?
So we recognize that tritium cannot be removed or processed the way that we are controlling tritium at the source. So in our waste acceptance criteria document, the revised document is on our website and will remain on the website. We do acknowledge there's different thresholds of, there's a criteria at which at a certain threshold of tritium being present, a concentration of tritium being present in our waste, that waste item now then has to go into a leachate controlled package. So that waste at a certain level goes into the package, so we're controlling higher concentrations of tritium in the waste from even contacting rainwater to begin with, so that it controls the amount of tritium that might be in the leachate. Those packages would have certain requirements to survive at least as long as necessary until the impermeable cover over a certain cell gets placed on it to continue that isolation from the environment.
Great. Well, thank you. So far, we have no further questions here. For our participants, I would encourage you to do a couple of things for us. As this is the first time that we've broadcast during the day at 11 o'clock, we'd like feedback on if this worked well, or you prefer an evening type of engagement. We're interested to hear your thoughts on that. I'd also encourage participants to continue to go to cnl.ca to check out the updated information that's available there as it becomes available. And then finally, I'll remind our participants that myCNL or cnl.ca or the YouTube channel has all our webinar collection, and so this is just another way to connect with the projects and learn a little bit more on the details associated with them. At this time, seeing no further questions in the queue, I think we'll call this a wrap. And thank you very much for taking the time out of your day to join us, and we look forward to hearing from you.
Thank you.
Great. Thank you.